Two statistical mechanics slides to go. These are quite important. So the aim behind all of the discussion that we've had over the last hour is to be able to calculate thermodynamic quantities. So we saw how you can calculate partition functions for individual forms of motion, but from those we can calculate a total partition function for the molecule as a product of the individual partition functions. And the total energy is obviously a sum of translation, rotation, vibrational and electronic motion, but that energy appears in an exponential. So when we consider the molecule as a whole as far as the partition function is concerned, it's the product that we're dealing with. So we're dealing with the product of the partition functions. And we had in the last couple of slides ways of calculating those various partition functions. Now, let's see how we calculate the thermodynamic quantities. So the molar thermodynamic energy U is obtained from the energy E, which is referred to the zero-point energy. So U is equal to U naught plus E. Now let's just try and understand what that means. So what we've got is a set of energy levels, and the energy is given by the sum of the number of molecules in each energy level multiplied by the energy of that level. Let's call it epsilon I. And so that's the energy of this molecule referred to ZPE, the zero-point energy. When we're looking at a reaction, then we need to refer to a common zero. So we might have another molecule whose zero-point energy was somewhere down here. And so we need to refer to a common energy zero. And so this is what we're doing here. So this is why we define a different quantity U, which is the thermodynamic energy. And we define that energy as being equal to U naught, which is the energy of the zero-point level referred to this common energy zero, plus n times, which is the total number of molecules, d log q by d beta, which is U naught plus nkt squared d log q by dt at constant v. So we simply need to take the partition function, take its logarithm, differentiate it, and then we can get the total energy. Very straightforward. The entropy is defined from the Boltzmann expression, S is equal to K log W. And if we've got gas phase molecules of the same type, then when they interchange their positions by translational motion, then we can't distinguish the initial situation compared with the final situation. And we need to take account of that in calculating the entropy. And so the entropy is given by U minus U naught here, so in other words, n d log q by d beta, plus r log q, and then we've got this additional term, minus r log na plus r. And that reduces the entropy because of this indistinguishability of the molecules. But we associate that indistinguishability with a translational motion. So if we want to differentiate between the translational entropy, the rotational entropy, the vibrational entropy, then we associate this term here only with translation, and we would remove it when we were calculating the rotational entropy. So a detail, but an important one. Okay, so U, S, and then the Helmholtz energy, A, is the constant volume equivalent of the Gibbs energy, the constant pressure. And because we're dealing with constant volume systems, in these StatMech calculations, then it's easier to work out A than G. So A is U minus TS, so we can work that out easily. You can also work out the Gibbs energy relatively straightforwardly, but what you've got to do then is to define the volume in terms of standard conditions. For our purposes, the most useful equilibrium constant is Kc, and Kc is, for a reaction of this sort, so that's stoichiometric number reactant equal to 0. We make the stoichiometric numbers for the reactants negative, for the products positive. So that's a simple schematic way of writing down the reaction. The equilibrium constant Kc is given by Qxi over V, so we take the volume term out, raised to the power nu I, e to the minus delta E naught over Kt, where delta E naught is the change in the 0-point energy going from the reactants to the products. So that's the total 0-point energy of the reactants, total 0-point energy of the products. And in working out all of these things, don't forget the electronic contributions. Okay, so just to keep you happy, there is a little exercise here. So you could pass that up, please. Oops. Taking a long time to come up, is it? Okay, has everybody got a copy? I would hate anybody to be deprived. Okay, so that's an exercise basically on OH or NO, recognizing that you've got two energy levels, you've got to worry about the energy spacing between them and the degeneracy of the energy levels. And what I want you to do is to work out, sorry, can I remember? Derive an expression for the partition function, then for the molar electronic energy U as a function of temperature, and for the electronic energy, contribution of electronic energy to the heat capacity. And sketch the electronic energy and heat capacity versus temperature. Remember, the heat capacity is the heat capacity CV will be equal to du by dt, and you're working out an expression for the energy. Okay, I'm sure you're going to be pretty shattered by this evening, so don't work on this any time beyond 3 o'clock tomorrow morning. But no, seriously, if you could just have a look at it and have a think about it, don't worry too much about working it out in detail. But what we'll do is we'll discuss it tomorrow morning, and it would be helpful if at least you'd gone through the motions of trying to understand what the issues are, even if you haven't worked it out in detail. Okay, it's a classic what's called a two-level system. And two-level systems are teach you an awful lot about partition functions and about distributions of molecules across energy levels. So what I'll do tomorrow is give you the answers as algebraic expressions, but the most important thing we'll do is to go through and understand what it means in terms of the heat capacity and the energy. Okay? So what I'd like you to try and understand by the end of tomorrow morning, what the energy and the heat capacity look like for this two-level system as a function of temperature, and what it means about the distribution of molecules throughout those energy levels. Okay, chemical kinetics. I think this is what we're supposed to be talking about. But, so in the time that remains, just let's have a little look at constructing chemical mechanisms and interactions between coupled chemical reactions. We probably won't finish this tonight, but we'll finish it off tomorrow morning. So constructing coupled differential rate equations from chemical mechanisms. So we've got a set of reactions. One or two people have asked this question: how do you decide what the mechanism is going to be? We'll discuss this on Thursday, but it's a non-trivial problem. But this is an example that we're just going to use. So the chemical mechanism is set up together with the associated rate coefficients, and then the coupled rate equations are then written down for each species. So for example, for H, we would have formation in reaction 1 plus K1 H2 times O2. Then it's used up in reaction 2, so minus K2 times H times O2. Produced in 3, produced in 4, used up in 5, used up in 6. So those are all the reactions that affect the concentration of H. And we write down an overall differential equation which includes all of those contributions. And I'm sure pretty well all of you have done this for some mechanism or other. And there's the oxygen atom system, a similar set of expressions, slightly less. And then you solve them numerically. And you might use a solver like Chemkin. And we'll discuss this later. And that's all relatively straightforward and to some extent a little mechanical. And what I want you to try and do is to think about what's involved and what the various things within this mechanism and this solution mean. And we're going to step through a couple of examples, simple examples now, to try to emphasize the interactions between different reactions. So let's make life easy for ourselves, and let's have a look at a set of coupled first-order equations. So these are reactions that just depend upon a single concentration term and are linear in that single concentration term. So it's a little bit unrealistic, but it helps us understand what's going on. And this is a sort of generalized matrix notation for that reaction. So we've got dC by dt, where C is an n-dimensional concentration vector, including the concentrations of all the species we're dealing with, C1, C2, C3, etc. And then that's dependent upon some function which depends upon concentration, always just to the first power, since it's first order, and a set of rate constants. And it's subject to a set of initial conditions, in particular this zero-time concentration vector C0. For a set of first-order reactions, we may solve using an eigenvalue approach, so we can write down the expression in terms of this term here, where M is an n by n matrix. If you've got n species, an n by n matrix of rate constants. It may be quite sparse matrix, but depending upon the size of the mechanism. And there are then n eigenvalues lambda of this matrix M, which are obtained from this determinantal equation here. And we also need the eigenvectors. And then if we solve those, we can get the time-dependent concentrations of Ct in this way here. And we'll use these ideas on Wednesday when we talk about master equations. These ideas are very central to a master equation approach. But we'll use them now for a couple of very simple examples just to show how the approach works. So let's just have a look at A goes to B goes to C. And they've got rate coefficients K1 and K2. So we can set up the rate equations, and to make life a little easier, we'll define the concentration of A as little a, concentration of B as little b, etc. And so we've got a rate equation in A. dA by dt is just minus K1A. dB by dt is K1A minus K2B. And then we can work out C by using conservation of mass. And that makes life easy because then we can reduce this to an M, a matrix, which is a 2 by 2. So always try and reduce the problems to a 2 by 2 matrix. So M takes this form. We've got these diagonal elements, minus K1, minus K2, which are the removal terms. We've got this term here, which is the production of B from A. And C, this concentration vector, sorry, not to be confused with that C, is the concentrations of A and B. We set up the determinantal equation, and we just get, it's going to be quite easy to solve because this cross term here is going to be 0. So this is the solution, minus K1 minus lambda times minus K2 minus lambda is 0. So lambda 1 is minus K1, lambda 2 is minus K2. And so that means that the concentration of A is going to be given by a constant times e to the minus K1t. That of B is a constant times e to the minus K2t, and the same sort of form for B as well. Now, what you could do is you could then go and look at the eigenvectors to get the full solution, but for a simple system like this, it's much easier just to look at the initial conditions. Just let's go through that quickly. So in particular, we've got that dA by dt is going to be equal to minus K1 times A naught. We've also incident, and that's equal to minus A times K1 minus B times K2. Just differentiating those two terms there. We've also got that A naught is equal to A plus B. But this is all we need because clearly B is equal to 0 because there's no K2 term over here. And so A is simply equal to A naught. And the concentration of A is simply A naught e to the minus K1t. So A just decays exponentially, as you would expect. And then you can find constants C and D by doing a similar approach, looking at the concentration of B at 0 time, which is 0, looking at dB by dt at 0 time, which is just K1 A naught. And then you can work out C and D. And so you finish up with an expression like this for A and like this for B. So B contains both of these eigenvalues, lambda 1 and lambda 2. And then C you can get by difference. Now, this is a very simple system, but it's quite an informative system because it tells us something really important in terms of a particular device that's useful to use in combustion. So, and that's the quasi-steady state approximation. So let's have a look at the behavior of this system. First of all, let's have K1 very much greater than K2. So that means that A produces B, and then B reacts quite slowly to form C. And we've got the solutions of A and of B. So there's a solution for B. A decays exponentially. always. And what's going to happen is that this term here corresponds to the buildup of B, and it occurs on a short time scale. And then B decays away quite slowly with an exponential given by K2. Okay? So that's the situation where A reacts quickly to form B, and then that reacts slowly to form C. Then figure B shows the situation in reverse, where K1 is now less than K2. So A is reacting quite slowly to form B, which then reacts quickly to form C. And so now K2 is bigger than K1, so let's reverse this term here. And we've got to reverse these ones up here as well. And so now what happens is that the buildup of B is determined by K2 and is very fast. And then it decays away with this rate constant K1. So B is now building up quickly and then decaying slowly again, but it's determined by a different reaction. Now the buildup is determined by its loss, and its decay is determined by its production. A strange situation, but one which arises because we've reversed these terms here. So B is again building up quickly, but determined by the high rate constant K2, and decaying away slowly, and its decay is now mirroring the decay of A. Okay? Now, supposing we've now got K1 very, very much less than K2, and let's look at times which are long compared with K2. So we can now omit this term here. B is built up, and we're simply left with B being equal to A0 times K1 over K2 minus K1 times the exponential of K1t. K1 is very much less than K2, so that's approximately equal to A0 times K1 over K2 times e to the minus K1 over 2t. And so that's exactly the same as the decay for A, except for this term K1 over K2. And K1 over K2 is very, very small. So what we've got then is that B mirrors A, it's decaying with A, but its concentration is very much smaller. So this is a situation with K2 equal to 50 times K1, and there's a situation with it being equal to 5 K1. And you can see that B now builds up to doesn't build up much at all. Its concentration is always small, always very, very much less than that of A. So B is very much less than A, but importantly, dB by dt is also very, very much less than dA by dt. And it's not a bad approximation to set dB by dt equal to 0, which is the steady state approximation. So we can use the steady state approximation in a situation where we have a species which is reacting much more quickly than it's being formed, on a time scale which is much shorter than that on which it's being formed.
You just assume that the formation of B is infinitely fast.
That's effective. The formation of B is infinitely fast. No, you're effectively assuming that the removal of B is infinitely fast. I mean, it's not, but that's the basis of the assumption that you're making. Is that reasonably clear? Maybe, maybe not. Well, how many of you have used the steady state approximation? Okay, so a few of you. And it is useful, isn't it? So this is a paper by a man from Hungary called Tomasz Tarani. I'm pleased to say he did this work in Leeds. And it talks about the error introduced by applying the steady state approximation. And it's a very interesting paper to read. It does help you to understand the steady-state approximation really quite well. And what he looks at is the error in the concentration of a species to which you're applying the steady-state approximation by applying that steady-state approximation. And that error depends upon dc by dt, but it also depends upon 1 over jii, where that's the diagonal Jacobian element, which is defined in this way. And jii is basically the lifetime of that species. So if this lifetime is very, very small, then the error in the steady-state approximation is small. So you can apply it to species which are reacting very, very quickly on timescales which are short compared with the overall timescales of the reaction. And here's an example. I mentioned earlier on the situation with pressure-dependent reactions. So let's have a look at this pressure-dependent reaction here. So what we're doing is we're taking a reaction, A reacting with B. And what they're doing is they're forming something which we're going to call AB star, which this is an energized molecule. It's a molecule with a lot of energy in it. If you want to look at it in terms of potential energy, then potential energy function looks like this. So A and B are coming together to form AB. And initially, they form a species AB star, which is up there. And AB star can dissociate rapidly, so it can come back out again, or it can collide with a third body and form AB. So that's colliding with a third body and coming down here. As I said before, third body is something like nitrogen or oxygen. Now, AB star is very short-lived, so there's going to be quite a small error in applying the steady-state approximation. So what have I called them? So this is Ka, this is K minus A, and this is Ks for stabilization. And so let's write down the rate equation for dAB star by dt. And that's going to be given by Ka times A times B minus K minus A plus Ks times M times AB star. And crucially, we're going to apply the steady-state approximation, and we're going to set this equal to 0. And the great thing about that is it converts a differential equation into an algebraic equation. So it's very easy to solve. And from that, we find that the concentration of AB star is equal to Ka times A times B over K minus A plus Ks times M. And the rate is going to be equal to the rate of forming AB, which is going to be equal to Ksm times this. So we've got the concentration of AB star. We want to form AB, so we multiply by the rate constant for coming down there. So we're going to get the rate is going to be equal to Ksm times Ka over K minus A plus Ks m times the concentration of A times the concentration of B. And this thing here is going to be the rate constant. So we've got the rate constant out of that by applying this steady state approximation. And there's the rate constant. And the interesting thing about it is what happens as we vary m. So let's make m very, very large. And so m goes to infinity. This term dominates on the bottom, so we can neglect this one. And the rate constant becomes equal simply to Ka. And we call that K infinity. And if we go for m going to 0, then this term dominates on the bottom. And we can forget about this one, and we get Ka times Ks times m divided by K minus A. And this is called K0 for zero pressure. And the rate constant now depends linearly on the pressure. And this is what I was on the concentration of m. And this is what I was saying earlier about this one here is effectively a third order reaction because it depends upon the concentration of A, of B, and of m. Whoops. Okay, so we can use these limiting values to get an alternative expression for the rate constant that's widely used. And we'll discuss this in more detail tomorrow and on Wednesday. Okay, so these are examples. So this could be CH3 plus CH3, OH plus C2H4. And we've made progress by applying the steady state approximation to AB star because it's very short-lived. Just thinking about it mechanistically, at high pressures, what's happening is any AB star that's produced is deactivated because the pressure is so high. So the collisions of AB star with AB star are so rapid that there's no time for it to go back out and regenerate A plus B. And so the rate determining step is the reaction between A and B. On the other hand, when we go to low pressures, most of these AB stars are coming back out again, and only occasionally do they get deactivated. So the rate determining step now is basically the stabilization. And it strikes me that maybe we ought to say a little bit more about rate determining steps, but leave that till tomorrow. Okay, any questions?
So I guess certain species you just wouldn't expect any chemiluminescence to be picking up like a...
Okay, yeah, that's an alternative mechanism of stabilization. Yeah, so what he's saying is that this excited species here might actually emit light and be stabilized by the emission of light. In combustion systems, that's a relatively slow process compared with stabilization. On the other hand, if you go into the interstellar medium, the pressures there, you just have 1 or 2 molecules per centimeter cubed. The concentrations are very low. And radiative stabilization there is very, very important. So yeah, that's a good point. An alternative to this is having radiative stabilization of these molecules. But by and large, it's not that important in combustion. Any more questions? It's only 25 minutes to go, guys. You must be absolutely shattered, are you? I didn't invent this format. I hasten to add. I think it's really tough on you. Okay, let's have a look at another example. And the change here is that we've made this first reaction reversible. Okay, so A reacts to form B, which can come back out to form A. And apart from the fact that it's nonlinear, this is that sort of process here. But we're looking at linear systems here. So we've got K1 and K minus 1 are the rate constants for these steps here. And so dA by dt is minus K1A plus K minus 1B. dB by dt is K1A minus K minus 1 plus K2B. And C, once again, we can get by mass balance. And the matrix M is now a bit more complicated. The diagonal elements, as always, are the rate constants for the loss of the species. These diagonal elements here are those JIIs that I told you about in this particular case because it's first order. So these are the reciprocal lifetimes of the species. And C is concentrations of A and B. So there's the determinantal equation, and this is what it turns out to be. And this is a bit more complicated. And so what we're going to get is a quadratic to solve, well, you look at it and you don't get, I mean, you could use it to calculate things, but you don't get a lot of understanding out of it. So let's put some limits on it, which are, or some conditions on it, which are reasonable. So let's assume that these two steps are fairly fast and much faster than this final step, B going to C. So K1 is approximately equal to K minus 1, which is very much less than K2. And then we can do a binomial expansion of this quadratic, and we get the lambda minus, the bigger of the two, is minus K1 plus K minus 1 plus K2. If you do a lot of these things, then that's always the case for K minus 1. For lambda minus, it's the sum of the rate constants when you do this expansion. And since K2 is small, that's approximately equal to K1 plus K minus 1. And lambda plus is this, which again, because K2 is small, turns out to be this here. So let's try and understand what's going on here. So let's start off by just let's let K2, well, let's let K2 equal to 0. So what we've then got is A and B reacting together, reacting reversibly, and B isn't lost. So it's what's called a conservative system. A and B is a conservative system. And they're basically equilibrating, coming together to equilibrate. So what's going to happen is that if we look at A, then it's going to decay like that. And so this is A0, and this is A infinity. And by difference, this is B infinity. And what's happened is they've equilibrated, and the rate constant for approaching equilibrium is the sum of K1 and K minus 1. And it's called a relaxation process. And a simple relaxation process like this always has the rate constant equal to the sum of the forward and the reverse reactions. And clearly also B infinity over A infinity is equal to the equilibrium constant, which is equal to K1 over K minus 1. So if experimental, and we'll look at an example of this tomorrow, if you experimentally measure this approach to equilibrium by looking at the rate constant for approach to equilibrium and looking at the long time ratios, you can determine the equilibrium constant. And since you have two determinations, you have this K and this K, you can determine both K1 and K minus 1. An important point to note here is that it's basically a 2 eigenvalue problem. The whole system is conservative, and so there are 2 variable species. We can express it as a quadratic. So it's a 2 eigenvalue problem, and if K2 is equal to 0, then the smaller of those 2 eigenvalues is equal to 0. And that smaller eigenvalue describes the equilibrium situation. So if you have a system like that, where you're approaching equilibrium, then the eigenvalue associated with that is going to be equal to 0. So there are still 2 eigenvalues, minus K1 plus K minus 1, and also 0. And the 0 eigenvalue relates to the equilibrium distribution. Okay, we're getting there. So those are 2 very simple examples. Let's now have a look at a couple of slightly more complex examples, which are important as far as our combustion considerations apply. So we're going to look first of all at chain reactions, and we're going to first of all look at straight chain reactions because they're a bit easier to understand. And chain reactions depend upon chain carriers or chain centers, and these are reactive intermediates. So things like H and O and OH. And they're generated in what are called the initiation steps. Propagation steps involve chain carriers reacting with the reactants to produce products and regenerate a chain carrier. So we have a chain carrier reacts with a reactant, produces another chain carrier and a product. And then finally, termination steps, where the chain carriers are consumed. And we're going to look at the hydrogen-bromine reaction. I apologize, I've slightly changed the notation here. I think I had news in your notes rather than R's, but I thought that might be confusing as far as stoichiometric coefficients are concerned. So I've changed the news to R's. So these are the rates of these reactions, R1, R2, R3, R4. And this is the initiation reaction where bromine dissociates by collision with a third body. And it's bromine that dissociates rather than hydrogen because it's got a smaller bond energy. So bromine is easier to dissociate than hydrogen. And then then we get the propagation steps. Bromine reacts with H2 to form another chain carrier, H, plus a product, HBr. And then H reacts with reactant Br2 to generate Br and form HBr. And so this is why it's called a chain reaction, because we started with bromine and we've regenerated bromine. So this is a link in an overall chain. And then finally, termination involves bromine atoms reacting together to form Br2. As we'll see, the concentration of hydrogen atoms is very small, and so they don't react together at the same rate, at anything like the same rate. So this is what the chain reaction looks like. So initiation, forming bromine, termination, removing bromine, and then these cyclic reactions here, bromine generating H and HBr, and H generating Br and HBr. And these are the links in the chain, the propagation links in the chain. And this is a calculation of the concentrations under conditions of 600K, 1 atmosphere pressure, and equal concentrations of hydrogen and bromine. We want to understand the difference in these concentrations here. So let's have a look at the relative rates after a second of reaction. So 600K, 1 atmosphere, R1 and R4, initiation and termination, they both have a rate of 1 unit. And they must be equal because we're not, in the steady state, we're not changing the overall concentrations of the chain carriers, and their concentrations are not changed in the propagation steps. It's only the initiation and termination steps that change their concentrations. So those concentrations, those rates must be the same. And R2 and R3, by contrast, are something like 100 units. So these propagation steps are 100 times faster under these conditions than the initiation and termination steps. So this means that this thing is whizzing round, and it goes around 100 times before it's eventually terminated by Br reacting with Br. That's what's called the chain length, the number of propagation cycles per initiation or termination event. And in this case, that's about 100. Now, let's look at this and determine the concentrations of the species involved. So let's write down the rate of forming and removing bromine. So it's formed in the initiation step, K1 times Br2, and there's a 2 in there because we formed 2 bromine atoms. And it depends upon the third body M. It's removed by reaction with hydrogen, produced by a reaction of hydrogen and bromine, and then it's also removed by the termination step. And there's again a factor of 2 in there because we remove 2 bromines when each of those steps occurs. Write down the same for hydrogen, and we just have these 2 terms here. And those are both equal to 0 if we apply the steady state approximation. And these bromines are reacting very, very much more rapidly than is either the H2 or the Br2. So this is a reasonable approximation. Okay, so what we can then do is add these 2 terms. These cancel out, and we've got the initiation is equal to termination. And so from that, we can get that bromine is equal to the square root of K1 times Br2 over K4. It's actually the equilibrium concentration of the bromine atoms. That equilibrium, once we've got into the steady state, is not disturbed by reaction because the propagation steps simply regenerate bromine. And then dH by dt is equal to 0. So from this, we can get that H over Br is equal to K2 times H2 over K3 times Br2. We're dealing with a stoichiometric system, so the concentrations of H2 and Br2 are the same. And so the concentration of H over Br is simply the ratio of those 2 rate constants, K2 and K3. K2 being this step and K3 being this step. The activation energy for reaction 2 is 82 kilojoules per mole. That for reaction 3 is 4 kilojoules per mole. So 4 is, their A factors are very much the same. So at 600 K, the ratio of the rate constants, and therefore the ratio of the concentrations, is about 10 to the minus 7. So the concentration of H is considerably less than that of bromine. And the dominant chain carrier concentration is that of bromine. And so we go back to this, what I showed you before. So there's the HBr being produced, and there's bromine in the steady state, hydrogen in the steady state, and a big difference between their concentrations. I'm going to now look quite quickly at branch chain reactions. But this is so important that what we'll do is we'll go through it again tomorrow morning. So but let's have a first stab at it now. Okay, so with branch chain reactions, for example, the hydrogen-oxygen reaction, in addition to initiation, propagation, and termination, we have branching steps where one radical generates 2 radicals. So this is H reacting with O2, forming OH plus O. One radical forming 2 radicals. Now, we can't handle this in the same way as we handled the hydrogen-bromine reaction. It's a highly nonlinear system because it can explode. So what we'll do is just look at a very simple way of looking at the total concentration of chain centers. So the total concentration of the chain carriers, the radicals, H, O, and OH. And that's going to be given, dN by dt is going to be given by the initiation rate plus the rate of branching, which depends upon the concentration of the chain center, minus the rate of termination, which we're going to assume for this argument, again, depends upon the first power of the chain carrier concentration. And so we can say that that's equal to I plus phi n, where phi is equal to G minus F. So phi is the difference between the termination and the branching rates. If we solve that, I is the rate of initiation. If we solve it, we get this. N is equal to I times the exponential of phi times t minus 1 divided by phi, where phi is the difference between initiation and termination rate constants. Now let's plot n over I. So this is the number of chain centers divided by the rate of initiation. Let's plot n over I versus time for negative and positive values of phi. So in plot 1, G minus F is minus 1. So in other words, termination is faster than branching. And so what happens now is A approaches a steady state where n is equal to I over phi as exponential of phi t tends to 0. So that's going to 0 because it's got a negative term. And so the chain center concentration approaches a steady state rather as it did in the H2Br2 reaction. On the other hand, if phi is positive, in other words, if branching is greater than termination, then branching is faster, and so this term now increases exponentially, and so the concentration of H goes up. And that's the basis of explosion in this sort of system. This isn't a thermal explosion. This is an explosion that arises because of branching reactions. Okay, so this is the hydrogen-oxygen system. And as you know, there are 3 explosion limits for hydrogen, which depend upon temperature and pressure. And the first explosion limit depends upon the size of the vessel and the quality of the wall. The second and third limits don't depend on these. Let's see what happens. Let's try and understand this. This is a slightly modified mechanism. And we've got this initiation reaction which we had before, H2 plus O2 going to H plus HO2. We've got these wall reactions and then 1 or 2 slight differences down here. But we'll just whiz through this and then look at it again tomorrow. But just let's look at the final consequences of all of this. So below the first explosion limit, the termination reactions at the wall dominate. So these reactions here dominate. Termination is faster than branching, and so we get no explosion. We reach a steady state. Between the first and second explosion limits here, then the branching steps, the propagation step and the branching steps 3 and 4 dominate. So we've got H plus O2 branching, OH plus H2 propagation, O plus H2 branching, and then OH, we produce an OH there. Let's allow that to react again to form another H. So if we add all these things up, we get H plus O2 plus 3H2 going to 3H plus 2 H2Os. So 1H is giving 3H. So we get explosion. And so, whoops, let's go back. So 1H reacts, forms 3 H's, and then each of those react to form 3 H's. And we get this exponential increase in the radical concentration of the explosion. Between the second and third limits, this termination reaction is important and dominates. So termination is again faster than branching, and we get no explosion. And then above the third explosion limit, life becomes quite interesting because we'll discuss this more tomorrow. This species here, HO2, we've said is quite unreactive. But what it does is two HO2s react together to form hydrogen peroxide, and the hydrogen peroxide dissociates to form radicals, two radicals, and we get branching. Okay. Thank you for listening. If anybody has any questions, then please come and see me now. But I think you deserve a drink. So see you tomorrow morning. Tomorrow afternoon, rather.